pleasure to welcome you to the SPRS Keynote Speaker Series, another session which is this time dedicated to creating digital twins of cities from data acquisition to analysis. And the presentation is going to be given by Bruno Vallée, by a French scientist who graduated from École Polytechnique and Telecom Paris Tech in 2004. He completed his PhD in the ALICE team of INRIA Nancy under the supervision of Bruno Levy in the field of geometry processing. After that, he joined IGN as a full-time researcher. Bruno Vallée successfully defended his research direction habilitation from Université Paris-Est in 2016. Since 2008, he participated in several French and European research projects. Since 2019, he coordinates the ACTE research team of the LASTIC lab at IGN in areas ranging from data acquisition, calibration, and registration to 3D scenes, reconstruction and analysis. He is also a co-chair of the working group of the second technical commission, working group number 4, which is a 3D scene reconstruction and analysis. And here I will hand over the floor to Bruno, and I believe you are looking forward for his talk.
Thank you very much, Lena, for the introduction. So, as I said, I'm going to talk to you about digital city twins, and I'm going to try to cover every part of the chain from data acquisition to 3D modeling. So, as an introduction, I started a bit by talking about what is 3D city modeling. So our purpose when we're doing 3D city modeling is to create a faithful digital twin of the city that is accurate in the sense that we want to have a low error, a low approximation between the model that we are building and the reality, which is both a relative question. We want to have accurate size for the things, accurate slopes. And we also want to have an absolute accuracy, which means that the data we are building is georeferenced, and we want this data to have a consistency with the geographic coordinate system. Usually when we're doing 3D city modeling, we're also doing some generalization. We're trying to adapt the level of detail of what is produced to what is required. And we're also doing things that are highly structured because the types of objects that we are modeling have this high level of structure. And then last but not least, we also want these 3D city models to be actual or up-to-date and to reflect the current state of the world and not something that is too old. So there is a standard called CityGML that allows to define this level of details for 3D city models. So you see they have 2 dimensions. One, the first level of detail goes from simple footprints to extruded footprints, then add the main structure of the roof, and then add all the superstructures of the roof. And they have a second level of detail that handles the really geometric level of detail of the representation. So in order to build things that are accurate, correspond to the reality, we need to acquire information on this reality. And today we're going to talk principally about acquiring image and LiDAR information on the scenes that we want to model. I also talked about radar because it's possible, but that won't be addressed too much in the talk. We're also going to talk about various acquisition platforms. And depending on the kind of monitoring that you want to do, and depending on the kind of level of detail that you want, your acquisition platforms can go from things that are very far, like satellites, closing in a little bit aerial acquisition platforms like plane and drones. We're going in this presentation to talk a lot about mobile mapping, because with mobile mapping, we're much closer to the actual scene and to the actual city. So mobile mapping is putting your sensors on a truck, a bike, a car, or we can also have mobile mapping on railroad, handheld imagery. Also fixed stations if you want to have things that are very precise. But of course, the compromise is that when you have things that are far away, you can have a coverage that is very extensive, whereas when you're going closer and closer, your coverage is very limited, and you're going to need much more time to cover the same area, the same amount of city. So once you have acquired the data, the first issue that you have is you need this data to be precisely georeferenced. And if you want to use data that come from various sources, in particular various modalities or various viewpoints that I've listed just before, or even if you want to combine your data with existing vector data sources, you need to register this data to make them geometrically consistent. And only at this condition will you be able to exploit the complementarities of your data. And then georeferencing is not exactly the same thing, even if it's linked. You can have direct georeferencing of your data. If your data has georeferencing sensors on the platform, I'll talk a little bit about that. But you can also have indirect georeferencing, and indirect georeferencing is registration between your data and a georeferenced source of data. So how to create digital city twins? The main aspects of 3D city models are generally can be decomposed into geometry, texture, and semantics. And my talk is going to address these various aspects of 3D city models. So geometry is the representation of the geometric description of the model. So you can have various ways to represent the geometry of a scene. So traditionally, we use 2.5D and digital surface models and digital terrain models to represent the geometry of the scenes we're interested in. But then there has been a shift towards real 3D with point clouds and surface meshes that allow to represent a much more general class of surfaces and a much more general class of geometries. So once you have your geometry, you can do two things. You can texture it, which is taking some radiometric information from images, but LiDAR also gives some radiometric information in order to add some visual content to this geometry. And then one thing that is often very interesting when you're doing 3D city models is to extract the semantics of your scene. So these are the main themes I'm going to talk about in my talk, and I will also talk a little bit about how do you do to update your models and to do change detection in order to do this updating. So finally, in this talk, I'm going to present some applications of these digital city twins. So I will talk a little bit about simulation, urban planning, inventory, itinerary computation, accessibility diagnosis, HD mapping for autonomous driving, and communication. So the first part of this talk is on data acquisition. So basically, a data acquisition platform may be a plane, a satellite, or a truck like displayed here, has three types of sensors that will allow to acquire information on the scenes that we're interested in. So the first type of sensor is the georeferencing sensors, the sensor that will tell us where exactly is this platform located in space. Then we can have image sensors and LiDAR sensors. You can have both on what we call hybrid platforms, or you can have platforms with only image or only LiDAR. So here I'm illustrating this on this vehicle that we call Stereopolis that we've had at IGN for over 10 years, and that was the basic platform for producing mobile mapping data for research. So here the three types of sensors. Here we have the inertial measurement unit that is in blue, the GPS that are here in green. We had two GPS on this platform, and we also had an odometer that measured very precisely the distance that the vehicle moved. And so all these georeferencing sensors, they produce some information that is going to be used and combined into a precise trajectory of this platform. So it's precise, but it's not perfect. When you're in a city and that you may lose some visibility of the satellite signal, then your system starts to drift, and you can have sometimes several meters of error between the trajectory that is given by the system and the actual real trajectory. So that's a problem we'll talk a little bit about. So then on this vehicle, we had LiDARs. So here, in this case, we have a planar LiDAR in blue and a rotating LiDAR in red. So planar LiDARs, for planar LiDARs, the LiDAR beams are fixed in the referential of the vehicle. And the type of data you can acquire with these fixed LiDARs looks like that. So you see that not only you have a very dense mapping of your surrounding area with a very high density of points, but you also have a precise radiometric information. So here it's illustrated in the decibels because you're measuring the difference between the quantity of light you have emitted and the quantity of light that came back from the scene. And you see that this information is quite fine, and it's also giving an additional information, an additional radiometric information to the basic geometric information given by the point coordinates. So here in this vehicle, we had also a Velodyne sensor. So Velodyne, the difference is that it's not fixed, it is rotating and it's covering a certain angular sector. And this point cloud that looks like this, but compared to the other ones, they are dynamic, which means that when objects move, you can see them moving in the data. Then in addition to these LiDAR sensors, we also have imaging sensors. So in this case, we had a panoramic head in blue and stereo pairs looking in front in green and looking back in red. So with all these images that you can acquire, once you have calibrated precisely these images, they give you an interesting radiometric information on the surroundings of the vehicle that you can aggregate this way. So this was an old panoramic head where the complete hemisphere was not covered. But nowadays, all the panoramic sensors that are used in mobile mapping cover the whole hemisphere. Here I'm illustrating some other possible platforms. So we've made more recently a car that is more compact, and even something called a roller, I think, that is even a smaller vehicle. And we always have all these type of sensors. Georeferencing sensors, LiDAR sensors, image sensors. So this covers data acquisition. Now I'm going to talk a little bit about registration. So once you have acquired all this data, if you want to build an accurate and precisely georeference model, you need to precisely georeference and register this data. So as our data is acquired by a platform that can, if the platform is static, the problem is pretty simple. You need to find a rigid transform, so a combination of a 3D translation and a 3D rotation that will put your data in coherence. But most of the time, our platforms are mobile, and when your platform is mobile, it's following a trajectory. And so, in fact, in particular, if you're acquiring LiDAR with your platform, then the problem of registration is in fact a problem of re-estimating the real correct trajectory of your platform. And if you have only image, you can only want to find one pose per image. But generally, the best way to handle things is to simply re-estimate the full trajectory, and then you will have both your LiDAR and your images that will be correctly registered. So as you want to register this, finally, what you do is you discretize it. So here in this example, we have discretized the trajectory with one transformation every second, and then the problem of estimating the registration of the trajectory is to find the accurate transform on each of these points, and then it is interpolated between the points. So this is an example of results when you're simply trying. So this is self-registration. So you're acquiring a point cloud, and you want that when you go twice in the same street or at an intersection, that your point cloud is coherent. So then you look for tie points between your LiDARs. and then you look for the trajectory that minimizes the distance between these type points. And so on the left, you have the result before registration, and on the right, after registration, and you see that on the right, the data is much more coherent. But then this data, you might want to register it on other data sources. So I talked before about a vector data source. So here we had a 3D city model, a pre-existing 3D city model that was well registered, but with a relatively low level of detail. And so what we try to do is to register some mobile mapping data on the low level of detail vector data, in order to be able to use this mobile mapping data to enhance the level of detail of the city model. So we did this also by posing the problem as a trajectory re-estimation, but this time what we were trying to minimize was the distance between the points. So we detected the facades in the point cloud. The facades were present in the 3D city model, and so we minimized the distance between the 3D points and the facades. Now there are other things that you might want to register, and in particular, if you're using image and LiDAR that was not acquired with the same platform, you might want to register data from these heterogeneous sensors. So we proposed very recently a line-based registration algorithm to deal with this issue. Why lines? Because lines are easy to detect both in image and both in LiDAR. They're easy to reconstruct from image, and they are precise as they aggregate information. If you're just taking a single LiDAR point, you have something that is less precise than if you detect a line that aggregates information from possibly lots of points. We propose a method based on RANSAC rather than ICP, because RANSAC is independent of initialization, and we want it to be independent of initialization in case that the images had no georeferencing attached to them, because we wanted also the algorithm to work indoors. And so we propose a method based on directional lines clustering, and then we, in RANSAC, you know that you draw randomly elements that you want to put in correspondence. So here it was pairs of lines, computing the corresponding 3D transform, and then we defined a robust distance between line sets. And with RANSAC, we finally choose the transformation that minimizes this distance between the robust line sets. So that's what it looks like visually. So on the left, you have a LiDAR point cloud and the 3D line segments that were extracted from the LiDAR point cloud. On the right, you have an image and the segments extracted from the image, and in the middle is the registration of these two line sets. And it appears that this methodology was also applicable to registering aerial and terrestrial images. So here we see in blue images extracted from a terrestrial acquisition, so images acquired by the mobile mapping system I presented earlier. And we also had aerial images, so with a good ground sample distance of 5 centimeters. And so we see that the coverage is very different, because, for instance, for the aerial acquisition, you don't have lines on vertical surfaces. You mostly have lines on horizontal surfaces. But because the method is quite robust, we were able to register the two line sets, and thus to register the two modalities, the two different platforms, aerial and terrestrial platform. Finally, in this work, we're also interested in registering inside data, because if you want to go to a very high level of detail on buildings, it's interesting to combine outside and inside data into a single model. So this is a rather hard problem, because you don't have much overlap between inside and outside data. So what we did was detecting openings in both scans, so detecting vertical rectangles. Then from the outside scan, we detected the points that were inside the building. So that's the points that were seen through these openings. And we also added the detection of planar polygons for the points that are inside, because in fact, what you can see through an opening is basically a bit of wall or a bit of ceiling, and that's a planar polygon. Finally, we used the RANSAC-based approach also to register these polygons and openings, and that's the kind of results we get. So that's the openings detection from outside. On the left, you have the openings detection from the inside. And on the right, you have the result of the registration of an indoor point cloud with an outdoor point cloud. So that covers some of our recent works on registration. So you see what interests us is combining both image and LiDAR data, so registering image and LiDAR, and combining various viewpoints inside, outside, aerial, terrestrial. So once all these things are covered, we can start using this data in order to analyze our scene and reconstruct our scene. And as I told you before, I'm going to cover the three main aspects of 3D CT modeling, so geometry, texture or radiometry, and semantics. And I will start by geometry. So the most common way we work with geometry and with geospatial data is with digital surface models. So they represent the scene in 2.5D, so they are a bit limited in what they are able to represent, but they are very compact and easy to work with. So that's why they have been very popular. So there have been traditional methods around for a long time, in particular the SGM method that is very popular to build these digital surface models. But recently what we have seen is that deep learning methods have been proposed to improve the quality of dense matching, and in particular in epipolar dense matching. So usually these methods, they are not really specialized for geospatial data or for DSM production. So if you want to integrate them in your pipeline, this requires fusion and resampling in order to use these methods in order to produce a DSM. And also you need to do fine tuning of the networks with a lot of geospatial spatial data. And basically these methods can be characterized in two categories. So they really try to address the full dense matching problem in a single pass or with a single network. And there are also hybrid methods that try to replace only a little bit, a brick of the DSM pipeline with deep learning. So here, what I'm talking about is has been published in the work by Wu Tang, which is a postdoc that works with me. So he has experimented a lot of methods. I'm not going to list them all, but here you have the detail of the different types of architecture and if they are hybrid or fully end-to-end. And we have also compared these methods with traditional pipelines like the Micmac software that is developed at IGN, and also a GPU implementation of SGM. So what are the conclusions that we've drawn from this study is that in fact with deep learning you can have very significant improvements on the quality of DSMs. So here at the top it's a traditional method, at the bottom it's a deep learning based method, and you see that in the error map you have much less error. You see, for instance, that the building outlines are much more precise, so it's going to be interesting for city modeling. The vegetation is less noisy, and you have a finer level of detail. But in order to get this significant improve of quality, you have a cost, which is that you need a very good training data. So when you're doing digital surface models, the training data is usually LiDAR, because LiDAR has the reputation to be more precise than photogrammetry. It's dense. So you need a good image LiDAR registration, so that we have addressed already this question of image LiDAR registration. You also need to predict occlusions, because usually the LiDAR is not acquired exactly from the same viewpoint as the images. So this means you might have occlusion issues to handle. And you also need to take into account changes, because if your LiDAR and your image has not been acquired at the same time, there might be changes in the scene. And in this case, you need to detect them and remove them from your training set, or you're going to learn bad things. Our conclusions was that also training data needs to be very diverse, because it is not practical to imagine that you will have, when you are building a city, that you will have ground truth for this city. So you need to have training data that is diverse enough, such that when you address a new city, the learning will still apply. So that's called the data set shift, and that's something that's studied a lot in computer vision. And we also studied the influence of the B-average, because we know that the B-average, so the ratio between the base and the height, is something that impacts a lot dense matching. And we found out in our experiments that the best thing to do is to do a training with that is well balanced in B-average. That is, you need to have a lot of examples of small B-average, medium, and important B-average. And then finally, among all the networks we have tested, we found out that the one that seems to perform best for geospatial data is PSMNet. So the result that is displayed here is a result from PSMNet. Now that was for 2.5D. What can we do if we want to 3D surface? A real 3D surface is usually represented with a surface mesh. And usually we ask for this mesh to be watertight because water tightness is very important for simulation and visualization. So building a watertight surface out of a point cloud has been studied that are used in the geospatial industry are either based on an indicator function, like Poisson reconstruction, for instance, that is very popular. And there are methods based on Delaunay, where you make that's what is illustrated here. You make a Delaunay triangulation of your point cloud, and then you simply label the tetraedras are inside or outside. And so the core of the quality of the surface you're going to get is how well are you able to label these tetraedras are inside or outside. Scaling up surface reconstruction is a hard problem because either you do tiling, but if you do tiling with overlaps, you cannot guarantee water tightness between the tiles. And so if you really want to handle the problem of reconstructing a surface at a very large scale, you need to handle an out-of-court Delaunay triangulation, which is not something that is trivial. And here I give the reference to a paper we have published last year that deals with this question. And here I'm displaying some results of this very large-scale surface reconstruction. And what I wanted to illustrate here is that one of the benefits of surface meshes is that they are able to provide a single geometric representation that combines various data sources. For instance, here, this was a reconstruction done on the city of Toulouse, and it combines a LiDAR acquisition, so all the roofs come from the LiDAR acquisition, and the mobile mapping acquisition, so only on a small area. It was to illustrate that we can integrate this information from the mobile mapping in the mesh and do a single mesh out of these very different data sources. So the color here illustrates the level of detail. So when you have a high level of detail, it's closer to blue, and when you have a low level of detail, it's closer to red. And so this means that we're also able to have an idea on what is the precision of the mesh on the various parts of the mesh. So this is a close-up on a small part, so you see that you can have a very high level of detail using these mobile mapping systems that are very close to the scene, and still have information at a very large scale with the aerial LiDAR. So this is a very recent production we did. Maybe you know that at IGN we have started covering the whole area of France with 10 points per square meter LiDAR. And so that's an experimentation that we did very recently where we use surface reconstruction on this data. So what's interesting, it means that in a few years, so probably by the end of 2025, we will be able to have this kind of description for the French, for the whole French territory. So that's something we're pretty excited about at IGN. Now the same question that we ask ourselves with digital surface models can be asked for surface meshes. Can deep learning help us to build better surface meshes? And so in fact, recently there has been many deep learning surface reconstruction methods out there, but most of them are adapted to rather small and closed objects and do not scale well, and so they do not apply well to the geospatial setting. So what we did with one of my PhD students called Raphael Sulzer, we tried to adapt a Delaunay-based method like the one that we've shown before, and just use the deep learning to learn the unary weights, so somehow to learn the probability that the tetraedra is full. So we proposed an approach based on graph convolution to aggregate all the different visibility information, because what's interesting and important for surface reconstruction is not only to have the point cloud, but also to know where each point is seen from, because this information is going to be very helpful to know if a tetraedra is empty or full. So this information is aggregated by the network. And we see that we've been able to improve on traditional methods. For instance, here we have a very difficult case with only a little bit of a staircase that is seen through an opening. That's the ETH3D benchmark. And with our deep learning-based methods, we've been able to correct the errors that were in the traditional methods. So that covers the geometric part of my talk, and how do you reconstruct the geometry of a city. Now I'm going to cover a little bit the texture. So what is the problem of texturing? Once you have from multiple sources that is sampled on this geometry, so you know what radiometry corresponds to what piece of geometry. That's the registration that allows you to tell you that. Now the question is, how can you merge this radiometry? So there are principally two ways to merge this radiometry into the geometry. Is either by blending. So when you have multiple sources, you do a kind of weighted average, but the problem of blending is usually you have something that is called ghosting. If you have a little difference between your two sources, it's going to appear a little bit transparent. And so what is mostly done to merge radiometry is mosaicing. So somehow that's how you build an orthophoto. You take various images and you mosaic your images. So when you have an arbitrary 3D geometry, you can still do mosaicing. That is for each piece of geometry. So for instance, for each triangle, if you have a mesh, you're going to choose one of your radiometric sources in a way that maximizes your quality and minimizes your seam lines, because seams are visible. Usually they are not very nice to see, and so you want to minimize them. So we've experimented a lot with texturing. So here we textured a LOD2 city model with mobile mapping imagery. Here it was an experiment where we replaced the visible image by a thermal image. And so we did that on all the city of Saint-Mandé, which is the city where IGN is located. So we had a company that lent us a thermal camera that we put on our Stereopolis mobile mapping system. And we used the texturing methods I described earlier in order to produce these thermal textures on all the facades. So it gives a much easier way to access this information than viewing hours and hours of videos, of thermal videos, because here the thermal information is put in the geometry of the scene. So I think that's an interesting product. That's a more recent experiment where we build a mesh from a LiDAR, mobile mapping LiDAR acquisition, and we use the images that were acquired simultaneously with the same platform to texture this mesh. And so this allows us to make these photorealistic models like this one. But what is interesting is that LiDAR also gives radiometric information. So I've shown it when I displayed an example of LiDAR earlier. And so in fact, you can also build a texture out of your LiDAR information. So in that case, you have an additional step that is rasterization and interpolation of your LiDAR. And then what we proposed was based on blending and not on mosaicing. If you look at what happens when you rasterize a LiDAR point cloud, so here a mobile mapping point cloud, it looks like that. So then you can do an interpolation. Here we use the Poisson equation to do this interpolation. And then we did a blending based on the distance from the point to the vehicle trajectory, and we obtained this kind of orthophoto that is a LiDAR orthophoto, and that you can produce everywhere where the mobile mapping vehicle went. And because you also have the geometry, because your LiDAR points already come with a 3D, then you can build this kind of digital elevation models for the road surface that is textured with the intensity of the LiDAR, and that's a product we believe can be interesting for some use cases. So now that I've covered texturing, I'm going to go a little bit towards the semantics. So how do you analyze the semantics of the data you have acquired on your city? So this I'm not going to cover too much. Semantic analysis of images is a topic that has been very extensively studied by the computer vision community. So there are lots of things that exist to do that, and we have not researched particularly this kind of thing. We just use existing networks. What we found really interesting was how do you do semantic analysis of LiDAR point clouds, because traditional networks use convolutions, and it's not completely trivial to extend convolutions to 3D point clouds. So we have a few works on that, but same thing, the computer vision community has addressed this issue, and now there are lots of very good point cloud semantization algorithms out there. And most of the time, the most important issue is having some ground truth in order to do a good learning. Now, very recently, we investigated the question, and okay, so we know how to do semantic segmentation for images, we know how to do semantic segmentation for point clouds, but in practice, if we have a point cloud and oriented images that see this point cloud, how could we combine all this information, both coming from both the radiometry from the images and the geometry from the point cloud, in order to have a combined semantization of all this data? So I have a PhD student called Damien Robert, who works with Loïc Landrieux as a supervisor, that have proposed a multi-view aggregation framework in order to combine both this image information from the images and from the point cloud. So the idea is that you're going to extract features from the images, you're going to extract features from the point cloud, and you're also going to create some additional features that carry the information on how well is the point seen by the image. Okay, so each different 3D view will carry a different insight, and you're going to have features that is going to tell you viewing conditions. So then they proposed an architecture that is quite simple. In fact, you have a 3D UNet to process the point cloud that is displayed at the top in purple. You have a 2D encoder to encode features out of the individual images. You have your viewing conditions that are also encoded, and the core, in fact, of the process is a attentive feature pooling that is going to weight these features that come from the image and the image that come from the LiDAR in order to produce the final semantics. So they have proposed 3 different ways to do this fusion, either early, directly on the features, or intermediate at the middle of the unit, or late fusion, that is after the unit. And it appears that what works best is early fusion, that is to really aggregate the features that are directly extracted from all the modalities. The results, in fact, if you look at the scientific state of the art on these topics, so many methods operate on colorized point clouds, so they are the top of the table. And when you try to operate on point clouds plus oriented images, you see that you can gain a little bit of quality, so it's not huge. But if you compare with the same backbone, so here it was, I think it was a KP-Conv backbone. If you compare with the same, you see that you have a significant improvement by working on point clouds plus oriented images rather than operating directly on uncolorized point clouds. So now the question we are looking at is, does this framework apply well to geospatial data with satellite or aerial imagery to exploit the fact that you don't have a single, usually people process orthophotos, but in fact, if you have multiple views of the same area, maybe you can take advantage of this multiple view of the 3D geometry you're trying to extract in order to have a better semantic analysis of your now also going to talk about this other experiment that is also quite recent that I did with my, that my PhD student Grégoire Jeskovic did quite recently, and he will present it at the NIST Congress in June. So our idea is that texture mesh, I've shown you a few texture meshes before, that are becoming more and more popular and mature, and there are more and more photogrammetric pipelines that are able to produce directly. So we are asking the question, can we directly semantize textured meshes? And it appears that there is a recent benchmark called SUM, and I thank the authors of this benchmark because the data is really interesting, where they did a semantic annotation of textured meshes on the city of Helsinki. And so we ask, what is the best strategy to address this issue of semantizing a textured mesh? So we looked a little bit into graph convolutions because a mesh has a graph structure, but the thing is that it also has a texture that has a different structure, and it was very complicated to handle all these different structures at the same time because there are triangles of varying size. Textures have very different size per triangle. Also, you have texture seams that were difficult to handle. And so, in fact, it appeared that the simplest strategy, and it was the best experimentally, was simply to sample points on the mesh to enrich these points with normals and texture that come, well, normals that come from the mesh and texture that comes from the texture. And then we used a reference algorithm with Péconve in this study to semantize the point cloud. So this is interesting because usually a point cloud semantization algorithm are a little bit sensitive to point cloud density. And here because we are able to sample things that has a very homogeneous density, we've been able to achieve quite good results. So here you see both the textured mesh, the sample point cloud, and here you have mainly three classes. Red is building, green is trees and vegetation, and the ground is in brown. And you see that you have a very accurate semantic analysis, 3D semantic analysis of your textured mesh. And then you can use this 3D information either to put it back on triangles or on vertices or even on textures if you I encourage you to see Grégoire's presentation in June. Finally, I'm going to talk a little bit about structured reconstruction. So what is structured reconstruction? Once you have geometry and you have semantics, you haven't done everything for 3D city modeling. In general, you want to reconstruct objects that have a high level of structure. So for instance, parametric objects from a library, for instance, road signs or road marks, are things that are highly structured geometrically, or you may want to reconstruct trees or buildings from a library. Or you may have very strong geometric priors, like you want to reconstruct a polyhedric object, which is an object that is made of planar polygons. So that's a prior that you often have on roofs. Roofs often have polyhedric shapes. Or you can also want to reconstruct objects that are derived from a grammar. So there have been lots of works on trying to make grammars to parse facades, for instance. And so reconstructing these higher level of structure objects is a difficult topic. So here I'm going to present a few works on this question. So that's work we did with Baman Soelian, where we wanted to build a library, let's say a data set of 3D road signs. So first you have to detect them. You have to also have a precise 2D geometry for these signs. And once you build this precise 2D geometry, you need to cluster these detections because you need to find out what are the different 2D detections that correspond to the same 3D sign. So in fact, that's the hardest problem in this pipeline. And finally, once you do that, you can find a parametric 3D road sign that minimizes the reprojection error in the 2D images. And once you've done that, you can build your parametric road signs in 3D. Another highly structured thing is what we call the navigability arrangement. So here is an illustration of what is a navigability arrangement. It's a decomposition of the urban space according to the mobility. So for instance, you don't have the same mobility on the sidewalks and on the road. And you even have these special objects that are the pedestrian crossings that are navigable by one mobility in one direction and by another mobility in another direction. So there has been a PhD thesis in our lab by Murat Hirsi that worked on how to prove it manually. But even manually, you have to handle this the partition that is already a bit complex, and providing the tools that allow you to handle both the geometric and the topologic aspects of these objects was already an interesting topic. There was another PhD by Rémi Cura that tried to produce such kind of navigability maps out of a database. So you assume you already know the road center lines, and you try to generate the whole surface out of the center lines by trying to fit the results to your data. Finally, I'm going to address the topic of change detection, because cities are very dynamic objects. So they change a lot. There are constructions, destruction, lots of things change in the city. So we addressed the question of change detection from a very geometric perspective. That is, how can you detect changes from a 3D geometry had by point clouds or meshes built from data acquired at different dates. So historically, there was some distance-based methods, but unfortunately, they did not allow to separate real changes from occlusions. If something was seen in one scan but not in the other, you thought it was a change, even if the geometry of the scene did not change. So in order to address that, we decided to think volumetric. So we know that when we acquire a point cloud, the space is empty along the ray. And we know that space is full where the ray hits something, so at the position of the point. And so, in fact, using this volumetric idea, we can detect real changes as inconsistencies. So you have space that is empty at one date and full at another date. And if this is the case, we are sure that it's a geometric inconsistency and not only an occlusion. So that's the work we led with my PhD student Wen Zhao, and this is the kind of results we get. Well, here we had two acquisitions at the same place. And you see that we're able to separate points that have no counterpart. So in yellow are points in one scan that have no counterpart, no corresponding information in the other scan, whereas the points in red are points that correspond to things that have really changed geometrically in the scene. And so you see that it appears mostly on vehicles, because between the two acquisitions, it's mostly the vehicles that had moved. This is a value of this methodology. I left on a dynamic LiDAR scan and right on another static LiDAR scan. Well, you see, for instance, here for a car, red means that the car has arrived, but blue simply means that these points were not seen in the first acquisition. So probably in the first acquisition, there was a car here hiding these points. And now, more recently, we investigated the question of could we do change detection with mesh? And the motivation behind is that we wanted to do mesh updates. We wanted to update meshes. And so we wanted to do change detection directly based on mesh. So basically, we used similar concept as the one I explained. So we use the distance-based method to find the consistent triangles, and then a volumetric method in order to that we extended to triangles on tetrahedras to separate occlusions from real changes. So that's the kind of results we obtained. So on the top row, you have the distance-based change detection method. So it already tells us that all the parts in gray are consistent. So we don't need to handle them in the second part that is a bit more time-consuming. So in the second part, we take all the pieces that are in red and we separate between what is a real change in the scene that is still in red and what is simply an occlusion, which is what is in purple. And so this gives us a very fine dynamics of the scene. So then once we did this fine analysis, we could tackle the question of mesh updates. So the first thing to do is we need to separate sustainable from unsustainable changes. So that's a convention we had, is that we considered that a change was valid if it was stable for more than 1 week, because we want in our databases, we are doing mapping here, and we don't want to map things that are not sustainable, things that move, like mobile objects or things that are, for instance, garbage cans that are here only 1 day and absent the following day. So first thing to do was to separate the sustainable from the non-sustainable part. So then when we had some discrepancies, we would discard the older, the older mesh parts that would conflict with a more recent sustainable change. So that's how you remove things that are not here anymore. And finally, the question that remained was, when you had consistent parts, how did you handle these consistent parts? You're not going to keep the various acquisitions of the same thing. but these parts, they do not coincide exactly. And what we propose to do with a 3D mosaicing, in order for the consistent parts to keep the parts that had the highest quality, so usually the ones that were scanned the better. But also we wanted to reduce seams because seams are displeasing. So that's so you have the data that was aggregated to do this mesh updates, and on the top is what happens if you don't pose the problem as a mosaicing problem. So you just keep the most recent data, but in the regions, then you have little pieces that try to fill in the holes. Whereas on the bottom, that's what happens when you pose the problem as a global mosaicing problem, and you see that you have much less small pieces. You're just trying to take the biggest pieces as possible from your sustainable mesh parts. So that's how we address the question of updating the geometry of a scene when you have regular acquisitions with various level of qualities. So finally, I'm going to talk a little bit about applications of 3D city models. So one of the standard applications of 3D city modeling is urban planning. So urban planning requires to have a precise knowledge of your territory. And in urban planning, you also want to visualize the impact of a project on your territory. So that there are some examples of how you can do that. You have also inventory. So usually when you manage a city, and in particular when you manage the urban furniture, you have to deal with lots of objects, and you want to know if the objects are still here. You want to know if they need to be replaced, if they have been damaged, if they need some renovation or modification. So for all these things, you need to have a very precise description of your city. So I talked to you a bit about that. If you have a very fine decomposition of urban space, then you can do itinerary computation for various kind of mobilities. Then you need these navigability graphs that can be produced out of these navigability arrangements I talked about earlier. This is another example of itinerary computation. You can also make accessibility diagnosis if you have a sufficiently fine description of the curbs and the slopes and the poles on your urban area. And one thing that is interesting in the context of autonomous vehicle is landmark-based localization. So earlier I talked about making a database of 3D traffic signs. Well, this was a work by Shu Xiaozi and Baman Suelian, where they used this database, and they shown that if you have this 3D database of traffic, you may have much precise localization. So on the left, you have a sign that is that does not use this database, and on the right you have the same SLAM but that can use these landmarks, and you see that the error ellipsoids are much smaller, so your localization is much more accurate when you have this kind of database. When you have a very accurate city model, you can do surveying from the office. So this accurately georeferenced data can replace going on the place to measure things, because you can do the same measures but directly.
I think we lost Bruno for a while. Let's wait if he is able to join us back. I tried to reach him via email.
Hi, I'm sorry for the inconvenience. I was disconnected. Can everyone hear me well?
Yes, we can now.
Okay, so I'm sharing my slides again. Sorry for the inconvenience. Can you see my slides?
Yes.
Okay, so I was almost finished anyway. So among the interesting applications of 3D city models is simulation. So you need, because the quality of your simulation is going to depend on the quality of your model. So for instance, interesting simulation is traffic simulation, noise simulation, flooding, for which you really need to have watertight surfaces, wave propagation, and finally, communication. People who build new projects like to have a 3D city model in order to show how their project integrates. So as a conclusion for this presentation on digital city twins, I wanted to talk a little bit about the challenges. One of the challenges of making very high resolution and high fidelity city models is to handle an insane amount of data. So usually, especially if you're using mobile mapping, you have terabytes per square kilometer. You have an important complexity of the scenes, so possibly you have complex 3D shapes, so we cannot work on 2.5D anymore. You have mobile and non-sustainable objects. You have radiometric issues where you have to correct shadows and reflections. And you also have problems with geolocalization, because in city, GPS and GNSS is usually highly unreliable. And so that raises important issues of registration. That's why I had a part on registration in this presentation. I wanted to talk a little bit about the maturity level. So acquisition is something that is very mature. It's not really research anymore, but it's still dynamic because there are lots of new sensors and new platforms. For instance, drones and sensors that have that are increasingly accurate and precise. Geofencing is more and more mature, but for mobile mapping, I consider it's still not completely, the problem is still not completely solved. For semantics, there have been a real revolution in the past years with deep learning, which allowed a really major improvement. And so it makes some automation possible, even if automation really needs a very high level of quality that is not always obtained by deep learning, depending on what exactly you're trying to model. And for scaling up with the big data and cloud technologies getting more and more mature, that helps us a little bit handling these massive amounts of data. On the final slide on perspective, I think that crowdsourcing is an interesting source of information that I have absolutely not covered here, but I think is really worth investigating. Map updating from low-cost data is also an interesting topic, because there's lots of low-cost data acquired every day with smartphones in cities, and how this data could help us having a more, at least up-to-date model is something interesting. Handling uncertainties is important when you want to control the quality of what you're producing. Coupling image and LiDAR, I have talked quite extensively about that. Coupling semantization and reconstruction is still a pretty open issue. Coupling aerial and terrestrial information is also something we have started to investigate, but that's still quite open. And also coupling inside and outside of buildings is something interesting. So I thank you for your attention. And if you have any questions, I don't see any questions in the Q&A. So yes, if you have questions, you can ask them in the Q&A or.
They are. You can see some questions in the chat.
Okay, maybe you can ask them because I don't see them. So
there is from Jan Schkalot at 1447. Hello.
Yeah, I think I don't have them because I was disconnected and I can't see the questions that were before I was disconnected. So if you can please ask them.
As far as Jan Schkalot, his question was, in the registration part, you have mentioned 1 translation per second. I wonder why not 1 per 10 seconds or 5 per 1 second? And finally, why not continuous? Thank you.
Yeah, that when I said 1 per second, it was more didactic. It was saying we sample the trajectory at a constant rate. So usually in our work, we thought that 1 per second was sufficient. In fact, the rationale behind it is that we know that the drift in the trajectory is very smooth. And so we consider we don't need more points because this amount of points is already sufficient. So that linear interpolation is a very, very good approximation to the real drift. So yeah, we could perfectly well choose a different sampling rate. It's a compromise. It's a compromise between computation time and precision. And 1 per second was the compromise we made, but other compromises are very, very acceptable. So yeah, I hope it answers to your question.
He's not allowed to answer, so I suppose yes, and he will probably reply.
Okay. So I see a question from Wenzhou. So I'm glad to see him. He was my PhD student for a certain time, and some of the work I presented was from him. So have you considered the moving components in cars, people? So usually cars and people, they are things we want to get rid of. So for several reasons. First, they are not sustainable. When you're doing mapping, you don't want to map cars and people. What we have done in a project a few years ago was mapping flows, which was producing maps of people flows. We put a Velodyne sensor on a very large place in Paris, and we were monitoring the flows. And another reason why we usually want to remove these things is that there are lots of issues on privacy, and we are usually required when we do mapping to remove anything that is private that can help identify someone. And so that's the reason why we usually all our works on the dynamic aspects of cities try to remove all these identifiable elements and objects from our scenes.
Thank you very much. I cannot see any other question. Time is over, so probably people are busy already. And I would like to thank you very much, Bruno, because you made not only a perfect overview of this topic, but you've made also such an open door for all who are invited to come to France, to Nice, to the 24th ISPRS Congress, which will take place in about 2 months in the beautiful city of Nice. And you are a member of the group whose headquarter person, Nicola Paparodidis, is a chair director of the Congress, and he has been working for 6 years for the preparation. And I would like to thank him. Thank you for your work, not only here during the presentation, but also during all years of your life, from which we saw the result. And this is my message on behalf of the ISPRS Council. And I am happy I could have participated in this meeting, and thank you and wish you all the best to all of you.
Thank you very much, Lena, for the invitation. Yes, this talk was also partly a teaser for the ISPRS Congress, because I didn't say it every time, but at least I think 4 of the works I presented very briefly here will be presented in much more detail by the people who led the work during the Congress. And so, for instance, all the registration, the line-based registration, also some parts on the change detection will be presented at the ISPRS Congress. So yes, I hope it's made a good teasing for the Congress, and I will be there, and I hope most of you in the audience we will be able to meet in Nice in June.
I hope so. So once again, thanks a lot and have a nice weekend.
Thank you, and see you all in Nice.
See you in Nice.